Hello.
Hi, good to see you again.
Nice to see you.
Same deal as last week. I don't, you seem to be the expert on these study sessions, so I don't really feel like I need to explain it. I'm just gonna give you co-host privileges as usual, and then I'll be in the background admitting people and things like that, and if you need anything.
Perfect. Thank you.
Um,
Hello, everyone. Welcome to today's session on Physics 1. I will start off the slides. As usual, we'll do slides and then passage questions. I also have some just like single questions after. I don't know if this one's going to run short or not, but let's see. Let me share the PowerPoint. So, welcome to Physics for the MCAT. This PowerPoint I actually made in the summer when I did Physics 1 and 2, but you guys are doing 2 tomorrow with Angel, so we'll only do half the presentation. So, like only from 1 to 5, I guess, today. We'll leave the rest for Angel. That being said, I'll upload the entire thing. And I think most of the slides are actually for the second half, so you have like 70 extra slides we're not covering. If you want to look at them, they'll be in the Canvas. So just starting off, with an overview for physics. I feel like physics kind of scares people sometimes, but it's not too many questions. It's going to be in the Chem Phys section, so it's going to be first up on your MCAT. But out of the 59 questions, the AAMC says about 25% of it is physics, so about 15 questions. You'll get a periodic table, but that's more like for like nuclear decay and stuff. So not the stuff we're covering today. You wouldn't need it. You do have to memorize the formula. You won't have a formula sheet the way you do in, I guess, college physics. But what's even better is to actually understand the formula. You won't have a calculator. So mental math becomes important, and I highly recommend rounding if you need, especially based on the answer choices. Usually the answer choices will be very far off in terms of numbers. You might have like 100, 500, 1000, 5000. And so if one of the numbers you're dealing with is like 190 and you round that to 200, that's not going to cause that huge of an issue where you won't be able to tell the answers apart. So yeah, definitely round for the mental math. And one good thing is there's no calculus. So as much as like the way we learn physics in physics 1 and 2 is calculus based, you're mainly just going to need algebra for the MCAT. I guess the biggest tip for physics that I can recommend before we get into the review is just like looking at units and understanding units. It can help you a lot. If all the answer options have the same units, then you kind of have a roadmap on what to do. Like if all the answers are in meters per second and you're given a value with meters and a value per seconds, you can tell that you're gonna have to like divide those in some way. Even better when it gets into things like pressure, like energy. If you know where the SI derived units come from, if you can divide that into like the base units, then you can just kind of tell how to arrange all your numbers to get from one thing to another. So for example, a joule is actually a Newton times meter, and that actually is kind of the work formula is like work is force times distance. So knowing units will help you a lot. So highly recommend that. Another thing is like graphs. If you're given any figures on the MCAT, look at the title and axis labels if it has. So axis labels, especially if it has units, then the idea of like slope and area can be important on that graph, and you can get a lot of information for it. So for example, this graph is like a velocity time graph. So it's like meters per second on the y-axis and seconds on the x-axis. What you can actually get from that is that like the area under would be like multiplying the two axes, right? Like length times width. So if you multiply meters per second times second, that gets you meters. And that actually is what like the area under a VT graph is. As you guys might know, that's the area under a VT graph is a displacement. And then slope, rise over run, is dividing. So meters per second divided by seconds is meters per second squared, the units for acceleration. And that is the case that the slope of velocity time graph is your acceleration. Or I guess the derivative if it's like a curve. So yeah, think about units in these as well. Slope and area can get you new values. So that's also nice. And then we move into content. So starting off with kinematics and dynamics. In this PowerPoint, I kind of have like screenshotted what the AAMC says is like covered on the MCAT. So to start off for like translational motion and equilibrium, they say like all of Newton's laws come up. Friction, static and kinetic, center of mass, vector analysis of forces, so just like your free body diagrams, understanding how forces work, torques and lever arms is the gist of it. So to start off, we have our 5 kinematics equations. I would say it's good to know all of them, as much as like memorizing equations might be tough, but also in terms of understanding them. We can only work under constant acceleration. So that's one thing. Like if you have like a changing force, then you have changing acceleration, then you can't use these anymore. So as you move into like dynamics, they might not work as much. But for kinematics, you can use these. And then there's 5 of them. What you'll notice is there's also 5 variables that come up in the equations. There's displacement, initial velocity, final velocity, time, and acceleration. And each equation has 4 variables. So on the right-hand side, I've written like which of the 5 it's missing. So in any problem, what the left-hand side is basically saying here, you're given 3 variables, you need one and you can forget one. So since there's 4 things, you'll be solving for one of them, which means you need 3, and you can just forget about one. The forgetting one is kind of a key thing. I pilot lead for physics, and I see a lot of kids like pick the wrong equation that has something that they don't really need to deal with. Like if you have initial and final velocity, You can be given these, by the way, like explicitly or implicitly. So you could literally say like final velocity is 3 meters per second, or it could say something like starts at rest, right? So you're gonna have to deduce that that means that the initial velocity is zero. If something's falling, then you have to know that acceleration is gravity, for example. That might not be explicitly told to you. But anyways, let's say you have like the two velocities and acceleration. You have those three, and they want you to find displacement. You can just ignore time. So you want to look at that bottom equation there that has no time. So like it's like a one-step thing. Another way is like I feel like people might use like equation one to solve for time, and then use a different equation to get displacement. But if you have three variables, you can get one and forget one. So just understanding that aspect of the kinematics equation, I think, makes them friendlier to use and makes a lot of problems into just like a one-step plug and chug. Next topic, center of mass. It's just kind of a weighted average, as you can see in the formula. So like your center of mass position will be like the position of whatever amount of objects you're trying to find the center of mass of. Object one times its mass, so position times mass, plus the position of object two times its mass, yada yada, for as many objects as you have, divided by the sum of all the masses. You can set anywhere as your zero, in the sense that like if you have a bunch of things, you could set like the left hand side as your zero and give everything a positive value relative to it. You can set like the center as zero, for example, and then like anything to the left of it is like negative, so like negative 5 meters and 5 meters. Or you could set like the right hand side as zero and be like negative 5 meters, negative 10 meters. That doesn't really matter, just be consistent on where everything is relative to whatever you're setting as zero. And I say, the importance of setting something as zero is that if you're multiplying by zero, you get to cancel that out. So that can come in handy when you're using the formula. So you can use that strategically, but then just like place everything else consistently. This is also the same formula. If you replace all the x's with v's, it'll be the same thing for like the velocity of center of mass as well. Forces, I'm sure we know Newton's second law, force is mass times acceleration. Force and acceleration are the two vectors here because mass is scalar, obviously, so those will have the same direction. It's also common forces that you can come across. As we probably know, gravity is mg mass times, gravitational force is mass times gravity. There should probably be an arrow on the g there. The spring force is kx, so the spring constant times how far you've moved it from equilibrium. Tension is a situational force, so you probably have to like solve that or it'll be given to you. There's not really a formula. And then friction is going to be the next slide. If you have a constant velocity, which also includes zero velocity as well, that means your net force is zero. And then for torque, the formula tau is F cross R, so force cross radius. It's good to know like cross products and dot products. So for cross products, it means you're taking the perpendicular portion. You'll notice in that formula, everything has an arrowhead. They're all vectors. If you guys remember the right-hand rule, your torque will be in like a third dimension compared to your force and radius. So know how to figure that out. And so for cross products, you're taking the perpendicular portion. In the example I have on the bottom there, if you have like a force at an angle to your radius, an angle theta, you can think of the perpendicular portion of either the force or the radius. So it confuses some people, but you can do either one, whichever one kind of works better for you. So the first one is like if you do F sine theta, you're taking the part of force that's perpendicular to the radius. So I took the diagonal force and thought about like which component of it is 90 degrees to radius and split it up that way. And then using the theta, you can figure out in the triangle that would be F sine theta, that red arrow. So I do the F sine theta times R. Or the other option is you find out what part of the radius is perpendicular to the force. And so that's that red arrow. Based on the triangle, you know that becomes R sine theta. So it'd be like R sine theta times force. Now it's sine theta in this example. It won't always be sine theta. So it's just know the perpendicular part. And then it could be a sine, it could be a cosine, but just like figure out a component of either force or radius that's perpendicular to the other one. And based on the situation, you may remember if you've taken physics one, like the weird torque problems and things hanging from things, it could be a sine or a cosine depending on what angle you get. So don't always, I guess, think that it's sine, but like in this basic example, it would be sine. Friction, another important force that's good to know. It is proportional to your normal force Fn. There's static and kinetic friction. And so there's two different coefficients for those. The coefficient of friction is that mu s for static friction, mu k for kinetic friction. So kinetic friction is when something's sliding. Static friction is when something is not moving, or if wheels are rolling. We'll get into that. The equation is an inequality for static friction, and that's because basically if you have something and you're pushing it, as you can also kind of see in the graph there, if you're applying a force on an object, let's say you're applying 1 Newton and it's still not moving, then your frictional force in that case, your static friction is 1 Newton. It's just canceling out. Then you apply 2 Newtons, it's still not moving, then your frictional force is just 2 Newtons and they're canceling out, the object is staying still. Only when you like break the static friction kind of and like the object starts to slide, that's when you've kind of reached the maximum. So the maximum on this graph, for example, is 3 Newtons. So like it'll just equate your applied force until you hit that maximum. And that maximum is what's equal to mu s Fn if you're to solve the equation. But then also at the maximum, once you exceed the maximum, once you apply more than 3 Newtons, you've kind of broken the static that's holding an object to the ground, and it'll start sliding. And at that point, your frictional force is lower, and the object is sliding because you're applying a force that's greater than the friction trying to hold it back. So it'll be accelerating forward. And so that kinetic friction is going to be constant. So no matter how much force you keep applying, it'll just be that constant. It looks like I don't know, 1.5, I guess, Newtons, even if you're applying like 4, 5, 6 Newtons on it. So hopefully that makes sense. The other thing I said about rolling wheels, if you think about a wheel rolling, it's not sliding. It's not like this. It's like each point is kind of touching and it has like static friction, then it's breaking that static friction if you think about something rolling. So every point to touch the ground is static, and then you break the static friction and then you just keep rolling. So that's why rolling wheels are static. That's a good thing to remember, I guess, a little piece of info. Moving into work and energy. Also, just if any questions appear at any time, put it in the chat or unmute, by the way. For work and energy, you want to know work done by a constant force, Fd cos theta, technically F dot D, we'll get into it. Mechanical advantage, work energy theorem, and conservative forces. And then for energy, the 3 formulas they want you to know: kinetic energy, half mv squared, potential energy in 2 different ways. There's mgh for gravitational potential energy and half kx squared for a spring. You want to know conservation of energy and power. It's also important, as they say, like comma units or semicolon units. So like as I mentioned at the start, understanding the units for everything is really important. So keep that in mind for all the different physics concepts. So work is F dot D. Dot product is the parallel portion. So cross product was the perpendicular. Dot is the parallel portion. So if we have the setup, the same direction of arrows, but it's like force and distance now, you're applying that kind of like downward force, but the object moved a distance across. If you have that theta, you want to take the part of your force that's parallel to the distance. So that's the red arrow there. That's also F cosine theta if you do the trig on the with the theta, and so then you'd have FD cosine theta. So dot products usually are cosine, but more important to know is that it's the parallel portion is what you're taking. Another thing to know with the cross product, it was like the right hand rule where like you have 2 dimensions and then you like get an answer in the 3rd dimension. For dot products, if you dot 2 vectors, it's a scalar. So work and energy are scalars. They don't have any directions, even though your force and distance do. So then energy, the 3 formulas. So kinetic, half mv squared. Do we know precession? I don't think so. It's not really on like the topics, the screenshots. I think that's a little beyond the MCAT. I think I never came across it in my practice or my MCAT at least. I do remember that was like a difficult concept from physics. There's not too much rotation in general in physics, like rotational motion and all that don't really come up, but they do mention torque, so good to know that. So yeah, for energy, these are the 3 main formulas. So kinetic energy, half mv squared. For potential energy, mgh, and then for spring potential energy, have kx squared, k being that spring constant again. And then with different formulas, the result will still be in the same units. So again, units always matter, units will always check out. Work is your change in energy. That's just a good formula to also know. So if you have like energy final minus energy initial, that's your work, that's your change in energy. And power, another concept, is work divided by time. So whatever change you can also, that means it's also change in energy over time. So like the power to do something is like how much did the energy change and how long did it take you would need. And then yeah, just like the units will always check out. So work, energy are all in joules. Then we move into thermodynamics. A lot of things here, but then like if it says GC, that's Gen Chem. So we did cover some of these 2 days ago, like enthalpy and Hess's law and stuff. But make sure you understand a good deal of thermodynamics, like the different laws and stuff. The main thing that's like physics out of here are like the coefficients of expansion and PV diagrams. So that's what I have in the slides. For a PV curve, it's good to know. So pressure volume curve, work is the area enclosed. So there's like different ones in these 4 examples here, but you would want to look at that like yellow area to see what the work done is. So it's good to know that those curves enclose that. In terms of heat transfer, there's kind of 3 main ways. There's conduction, direct contact, or like if you're thinking wires and stuff. Convection, the motion of fluids. So like if you're thinking a convection oven, or like you're heating something up on the stove and it's like that heat rotating around in your like pot of water or whatever. And then there's radiation, like the sun's heat or electromagnetic radiation. Fluid also, by the way, is a gas or a liquid. I think some people think of only liquids with fluids, but it could be either. Anything that flows. And then expansion, this does come up. It came up on my MCAT, I guess. That's why I feel like it's important, but it was never really taught in physics 1 and 2. So it's good to know that change in temperature can change an object's length or volume. And so then these are the 2 formulas for that: change in length, so delta L, or volume, delta V. The mnemonic, I guess, is just a lot. That's kind of what it looks like, but it's alpha, L, delta T. So alpha and beta there are your coefficients of linear expansion or volumetric expansion. That'll just be like a number given to you, or if everything else is given, you will solve for that. It's also interesting to note that beta is just 3 times alpha. So you can think about like if something's linearly expanding, your coefficient is alpha. If it's a volumetric expansion, it's just like linear in 3 dimensions. So you can multiply that alpha by 3 to get your beta. Interesting to know. So basically your change is your coefficient times that original length or volume times the change in temperature. So good to know if you have something expanding. It was like the second question on my MCAT. I was like, I never thought this would come up, but there it was. And yeah, that a lot mnemonic is also good. And then fluids, which is I guess the last topic that's like physics 1 related. What they ask for here: density, buoyancy, hydrostatic pressure, viscosity, continuity, surface tension, Bernoulli's, and like the Venturi effect. It's just kind of like that last chunk of physics 1 that they do after waves. So for hydrostatic pressure, it's the pressure exerted by the weight of a fluid above a certain point. So P is rho GH. You want density, you need gravity and height. So basically it's a pretty straightforward formula. Osmotic pressure, I mentioned this in Gen Chem, but I don't think I covered it well enough, so here it is again. Pi is I MRT. It's a spin-off of the ideal gas equation, PV equals nRT, where your obviously RT is the same thing. And then if you rearrange PV equals nRT, P is kind of like nRT over V. So that N over V is represented by your IM kind of. And then pi is like your osmotic pressure in atmospheres. So M is the concentration, so like the molarity, RT, gas constant temperature. That I, the Van 't Hoff factor, I guess I didn't explain this in Gen Chem, I just called it the Van 't Hoff factor, but it's the number of species the molecule dissociates into. So if you have something like sucrose in the diagram there, it doesn't dissolve, so it'd just be 1. But if you had NaCl, it dissociates to two ions. So that would be two. If you had, what is that, CaCl2, then it dissociates into three ions. So that would be three. So that's an interesting equation, I guess, that's testable on the MCAT. So good to know. Continuity, the equation is just like A1V1 equals A2V2. The concept behind it is that like your flow rate, your volume per time has to be constant. So A times V, right? You have like, say, meters per squared times meters per second is really meters cubed per second. So that's your volume per time that's passing. And that has to be constant for something incompressible. So like if you have a liquid flowing and at one point you have like 5 liters per second flowing, for that to be like a constant flow, you can't have like 3 liters per second flowing at another part and then like 8 liters per second at another part. Like it has to be a constant amount passing because you can't compress the fluid. So it's like it has to be the same thing passing the whole time. And so for that volume over time to be constant, if you reduce your area, like the cross-sectional area, then you will have to speed up so that the same amount can pass in the same time. So AV equals AV. If you reduce your area, you increase your velocity. If you increase your area, you reduce your velocity. So just good to know that like it's an inverse relationship between area and velocity for like a liquid flowing in a tube. And then we get to Bernoulli's equation. So there's 3 components: static, dynamic, and hydrostatic pressure. And that whole thing stays constant along a streamline. So like as something's flowing. So static pressure is just P, the fluid pressure. Dynamic pressure is like the kinetic energy, so rho v squared over 2. So the density times velocity squared in half. So it's kind of similar to like the half mv squared of our kinetic energy for like a discrete object. And then hydrostatic pressure is rho gh, as we covered. So that all is constant. So you could just say like P1 half rho v1 squared plus rho gh1 will equal to P2 half rho v2 squared rho gh2. So like if you're comparing 2 different points, that will be constant. An application of this is the Venturi flow meter. You might have seen in physics, maybe not, but basically as the tube narrows, as we covered with continuity, the tube will narrow, so the speed has to increase when you have lower area. And that means the pressure exerted on the wall increases, or sorry, decreases. So speed increasing, pressure on the walls decrease. And then that causes the column, because it has like columns coming up, to have a lower height at point 2. So interesting application, interesting device there. And it's just an application of that equation. Another concept, surface tension. Water, for example, has high surface tension. It means like there's like strong attraction between the molecules, and so you can have like a low surface area, and that's why water can kind of form droplets. But something with a low surface tension, weak attraction, so it kind of spreads out. With high surface area, probably won't be able to form like a droplet the way water does if something had a lower surface tension. And then gases, mostly covered in Gen Chem, I think. I don't know if I have, yeah. Okay, so just good to know because I guess it's like kind of between Gen Chem and physics, but I think most of it was in my Gen Chem PowerPoint, like Boyle, Charles, Gay-Lussac, those laws, kind of like the theory and stuff. So just heads up that these are on there. I guess we did kind of talk about them already in Gen Chem. After that, we move on to kind of physics 2 stuff, electric and magnetism. So now I'll pause if there's any questions. Otherwise, we can move into the passages that I have. Okay, if not, I mean, still feel free to put them in the chat at any time. But I guess we can move into the passages. Kind of shorter passages, but you may be familiar with the drill. I'll give you guys more minutes for the first one to read the passage and everything, and then 5 questions, I think, 2 passages. So we'll run through the 10, but put any questions in the chat at any time. We'll do 30 more seconds on this question. Okay, question 2. Thirty seconds. Okay, question 3. Thirty seconds. Okay, question 4. Thirty seconds. Okay, and then final question. 30 seconds. Okay, so I'll start taking this up. So for the portion of the trip where it's constant velocity, you don't have any acceleration going on. So the scale of reading will be accurate, I suppose. So it'll be like just equal to the weight of the copper. It's only when you have acceleration that things start getting kind of wonky. The mass of the copper is 30. Oh, I should probably keep the graphs in these. Let's just go from here. So the mass of the copper is 30 kilograms, and you find that from when it's not accelerating. So just kind of when it's still, it's at that 300 newtons, and you're using gravity as 10 meters per second. So that 300 newtons is when you're getting an accurate reading on your scale. So it's just mg is 300 newtons, g being 10. You divide that out, so you have 30 kilograms. The next one, the magnitude of the acceleration between 2 and 3 seconds is 3.3 meters per second squared. And so basically you have your acceleration of the entire elevator as well as like your gravitational force. So those two things combine for your net force. So basically what you're getting is that like the force on your scale minus mg is the ma of the elevator, since they're kind of going in different directions. So you'll have at that point between 2 and 3 seconds, you have 400 newtons. You just subtract like the 300 newtons being from the mg, so it's that 100, and then you divide that by 30 kilograms again that we know. And so the 100 divided by 30 is 3.3 meters per second. In a similar manner, for this question, it's 1.7, positive 1.7, because they asked for the magnitude. So as much as it's in a different direction, if anything says magnitude, you won't be giving a negative answer. So it'll just be 1.7, and you can see from the 8 to 9, or I guess 8 to 10 really seconds there, you have that gap of 50 newtons, and then divide that by the 30 kilograms. So that would be the answer for that one. And then the last one, the portion of the trip where they'd feel the greatest discomfort is when it's like the highest force that they're experiencing. So it'd be like when the normal force is the greatest, and that would be when the acceleration is going the greatest in the upward direction, and that's when it's the 2 to 3 second time period. You can also maybe draw from your own experience on an elevator. When you're going down, you feel like a weightlessness. When you're going up, you kind of feel heavier, or something's pushing up on you. So that's kind of what they're alluding to there. It's like that would be the part, I guess, where their knees would feel the pain the most. So it'd be the 2 to 3 second part. Any questions about those? If you do, continue to feel free to continue dropping them in the chat. No, I didn't even put the answer on this one. Otherwise, we can move to the second of the two passages. This one is about fluids. 30 seconds. Okay, question 2. Thirty seconds. Okay, third question. Thirty seconds. Next question. Thirty seconds. Okay, and final question. 30 seconds. And also, if you need a hint, because it wasn't in the slides, gauge pressure is the pressure relative to atmospheric pressure. So you would subtract atmospheric pressure from pressure. Okay, getting into this one. So the correct ranking would be V3 being the greatest, then 2, 1, 4. I guess just one of the tricks also, if you notice, like the first one is different for all of them. So really all you need to do is figure out the first one. And then, so thinking about where the velocity would be the highest, it's where the, can I go back? It's where the area is the lowest. It's that continuity equation, right? A1V1 is equal to A2V2 equal A3V3. And so where that cross-sectional area is lowest, velocity is the highest, and that would be 3. That is the narrowest part. And so just knowing that 3 will be the highest velocity is enough to pick that choice. Comparing pressure at point 2 to point 4, the pressure at point 2 will be smaller because water is moving faster there. So the fluid is moving faster at point 2 compared to 4. If we go back, I really should have just kept the drawing in the slides with the answers. Yeah, faster at point 2 because it's narrower and it's at the same height, so height wouldn't factor into this. And so then Bernoulli's principle says, like, if height's not a factor, the pressure will decrease if the speed increases. So hence it'll be a smaller pressure because the velocity is greater and the velocity is greater because the area is smaller. So it's kind of back and forthing through all those things. The speed at 0.3 and 4. So the thing to know about this is you are given the radius, and then it's good to know that radius is squared relationship with area. So the speed at 0.3, so you're given speed at 0.1 is 8 meters per second. The radius there is 0.5. The radius at 0.3 is 0.25. So the radius is halved, which means the area is quartered because that's squared relationship. And that means so it's 4 times less area, it has to be 4 times more speed to keep that AV equal. And so 4 times 8, it's going to be 32. You do a similar thing to 4. I don't know if 32, oh yeah, the 32 is enough to solve it. So that's another thing with like these questions sometimes is like you could do the work to find V4 as well, but just knowing V3 is enough. So take a second to look at the answer choices and figure out like what do I really need to know? How much do I really need to solve here? Possible pressure at the fluid for 0.3. So kind of ties back to this question as well, in the sense that for 0.3, you're going like the fastest, it's going to be a larger speed and hence a lower pressure because again, same height. So as speed increases, pressure will decrease. And so for that, you would get the lowest number here. Not just the lowest number, actually, the only one that's lower than pressure 1, because pressure 1 was 220. Yeah. So 220,000 pascals is the same as pressure 1. You'd have to be lower than that. So that would be the 160,000. Another thing to know is like just kind of deduction skills. If you're like stuck and you don't really remember the relationship, you can kind of look at the option choices and like the way it's worded is like what would be a possible pressure given the information. Like it's not really like what's the pressure. So in that case, you know that 220 is the same as 1. You can probably deduce that's going to be different from 1 just because like the like thing looks different. And then A and B are both higher. So even just from that deduction, even if you don't really know if it's supposed to be higher or lower, there's only one option that's lower. So that's an interesting part. And then gauge pressure, like I kind of said, it's the pressure relative to atmospheric pressure. So you just kind of like subtract out atmospheric pressure for everything. One thing that's good to know, I guess, because here they didn't give it, I don't think actually. Atmospheric pressure, so 1 atmosphere is equal to 101,325 pascals, so 101,325, but you could take that as roughly like, well, you could take it as roughly 100,000 and just figure out the closest one. But I think they actually did it as 101,000. So the 220 minus 101 would be 119,000 pascals. But again, the answer choices were far enough. Like for the mental math we just did, minus 100,000, you get 120, and that's obviously the closest to 120. So that is, I think, the last question there. I have some like discrete questions just to like work on practicing the formulae. How are we for time? Okay, yeah, we can do them anytime. Unless there's anything anyone wants me to cover, if you want to like unmute or put in the chat, or if there's any physics 2 topics, because technically I have the slides that you just want to like preview or you really want to learn about. Otherwise, we can do these questions. I don't know if there's any preference on questions versus more content. Lenses. Sure, we can talk about lenses. Let me reshare the other PowerPoint. And yeah, again, I actually don't know how Angel structures her session, so I don't know if it's like a lot of slides and content or if it's more review. But that might come up tomorrow as well. Did I share the same thing again? No. Can you guys see? Does it say light and optics? Hopefully. Okay, let me know if it doesn't. But so for light and optics, these are the different things they want you to know. So getting into it, there's like electromagnetic waves, visible light, the speed of light. Oh yeah, I had some like questions in the middle there, but we want to get to lenses, diffraction, refraction. So, well, I guess we can start with plane mirrors are like the simplest because angle of incidence is equal to angle of reflection. So it's just equal angles there. Spherical mirrors, you have a focal length that's like half of the radius of your curve. Like if you were to make that curve into a full circle, you have your radius, half of that is your focal length. And so you have different looking images there, and you just want to take that focal point and you either draw a ray that will go like parallel, like straight, and then bounce back and go through the focal point, or go through the focal point and then be straight after, as you can kind of see in the diagram. So it's mirrors, and then yeah, best way to understand is to draw them out yourself, I would say. But when you're using the equations, there's like sign conventions to know. So for like your object image, concave versus convex, you want to know what like positive and negative are, like how that translates into the equation. So like for an object, if it's in front of the mirror, you put it positive, like that distance. Very rarely is your object behind a mirror. So for your image though, it could be in front or behind, but if like your equation's giving you a positive number, it means it's in front of the mirror, it's real. Behind the mirror, virtual, would be a negative answer for your image distance. For your radius of curvature and your focal point, for a concave or converging mirror, it would be positive. It would be negative for a convex or diverging mirror. So these are things that like basically become memorization, just like knowing that stuff. And then for your magnification, the image will be upright if you get a positive answer, inverted if you get a negative answer. So like positive 2 just means it's like upright, 2 times bigger, negative 0.5, it's like 0.5 times, it's like half the size and it's inverted. So these are ray diagrams for concave versus convex. So again, good to know about like the concave versus convex, which looks like what. And then, like I kind of said, you want one parallel and then one through the focal point. And I think after that is lenses. Yeah, okay. So that's mirrors. Lenses, similar, but you actually kind of flip the sign convention a little bit. So a convex lens is converging and a concave lens is diverging, which is interesting. And then magnification, high over ho, negative di over do. So it's height of your image divided by height of your object, or negative distance of your image, distance of the object. And you also have your thin lens equation, where 1 divided by the focal point is the sum of 1 over the object distance and the image distance. So all good equations. I have a practice question about lenses here if we want to try that in the dying minutes. I'll give maybe a minute 30 to solve it. Hopefully that's sufficient. Okay. Does anyone want to explain or think they have it? Okay. If not, it's the one third. So basically, it's that equation like your high over ho, die over do. And so what you're going to be taking is the ratio of the object to image distance is also the ratio of the object to image height. So the image, so you're given the distances 4f and 4/3 f. So you would divide, so 4/3 f divided by 4f is a third. And so that would mean that 1/3 is your ratio of the height of the image to the height of the object. Yeah, just make sure that you're keeping the corresponding things tracked in your head. So like if the you're dividing image by object, so 4/3 divided by 4, so you get the ratio of the height of the image to the height of the object. So you still want to do image over object both times. In terms of the negative in the equation, it's because your image is inverted technically. So if you're keeping track of the negatives, but you can also kind of just see that none of the options have a negative, so you don't really have to worry about that in this case. Do you have any other questions about lenses or any other topics anyone wants to talk about? I guess we don't have too much time, but I can preview slides on anything else if there's like certain physics 2 things we want to go over quickly. But if there's no other questions, I guess you can get 3 minutes. But I don't know. I feel like I hate when people say that you get like 3 minutes back, but that's all I have for today. So stay behind if you have any questions. But otherwise, thank you all for coming.
Hello, hello. Thank you again, as
Hi.
always.
Is
Great.
that a cat?
This is my dog. He
Dog. Oh, I
behaves. He
cannot see
behaves
from
a
here.
lot like a cat, but
Oh, so cute.
his name's Yari. Look, Sarah.
Hi.
But yeah, thank you so much as always for all of your work.
Yeah,
Ryan,
no
you
problem.
sticking around to ask a question, or are we?
Any questions, Ryan?
Oh, there we
No.
go.
All right. Thank
All
you.
right. Have a good night.
You
Bye.
too.